Can you see my screen?
Yes, sir.
So we have already completed with various topics on digital image processing pertaining to your enhancement, geometric, radiometric correction, filters, then low pass, high pass filters, then band rationing techniques like NDVI, NDWI, MNDPI, NDPI, MDTI. So we have done with major of the transformation index like Fourier transportation principal component analysis. So we have completed the major topics of interest. Okay. So today we'll start up with a new topic that finally you have got a satellite image, you have corrected the data geometrically, you have corrected the data radiometrically. Now you have rectified the data in terms of contrast, all the errors pertaining to your climatic condition, radiometric errors you have rectified. You have applied various kinds of filters to improve its visibility, whether you want to highlight the homogeneous features or heterogeneous features. And finally, today, your all the data sets are ready. Now you have to classify the data set. Now, how to classify the data set? In order to classify a data set is providing a class value to each and every pixel of an image. To more precisely, what we are trying to do in digital image classification, we are providing the class value of that pixel key for which class that pixel belongs to, whether it belongs to build up, whether it belongs to wasteland, whether it belongs to forest land, whether it belongs to wasteland. And gradually those pixels will combine together to form a clusters of various landforms, clusters of various land cover, clusters of various land use. So we are going to classify each and every satellite image, each and every pixel. None of the pixel must be unclassified. You have to classify each and every pixel. Each and every pixel corresponds to a specific earth feature. So if you are not providing the class value or the class name to that specific feature, means you are undefining the area, you are leaving the area blank. So using the spectral information represented by distal number in one or more spectral bands, we are going to classify each and every individual pixel based on its spectral information and also known as spectral pattern recognition. So what we are trying to do in digital image classification, we are trying to identify the digital image pixels. We are trying to identify the spectral pattern. So the objective of the present topic is to assign all pixel in image to a particular class or a theme. So what is our motive whenever we are getting any satellite image? The motive is to classify that satellite image. Final product of any satellite image will be a classified image. So what we are trying to do, we are trying to classify it to any particular class or theme, that is whether that is a water or coniferous forest or deciduous forest or crops, barren soils, each and every landscape. So when we are trying to say digital image classification, we are trying to, as you already know that in Landsat thematic mapper, you have got 7 bands that start from TM1, TM2. They are the thematic band blue, green, red, near infrared, middle infrared, and last is thermal infrared. And you can see how different spectral response curve of those bands when you will be plotting that with the pixel value, how different bands behave differently in a spectral response curve, and you can see the average rasters value of each and every band that is corresponding to. So we'll be using this band values like when we generally see the color, but if you go to the background metadata, you will be finding the base value that are enclosed in each and every band, and that is in the form of pixels, and they are the multi-spectral channels. So you can see that what we are making generally we have got three guns, blue, green, red. So we'll be passing those bands, 7 bands, with this three bands, that is blue, green, red, will be passing through that in order to get a composite band, that is the band value 4, where you can we also say that as a false color composite. And on the basis of that false color composite, we are going to distally classify the image, and you will be vector rasterizing it, you will be providing the signatures, you will be forming the clusters to finally classify the image into various land use, land cover categories like residential area, commercial area, transportation network, green area, forested area, minerals, organic soils, and water. We'll be classifying the satellite image. So how do we do this digital image classification? So there are two approaches through which you will be doing your digital image classification. The first one is per pixel classification. What do you mean by per pixel classification, and what do you mean by object oriented classification? They are the two approaches that we use for digital image classification. In the first, the algorithm characterizes each input pixels into a spectral feature class based solely on its individual multispectral vector, that is signature. No context or neighborhood evaluation is involved. So per pixel classification means we'll be taking each pixel, and on the basis of a spectral class or a spectral value, will be classifying it individually using the multispectral signatures. And in object-oriented classification, the input pixels are grouped into spectral objects. Here we are making signatures, here we are making objects using image segmentation algorithm. So what we do, we make image segmentation algorithms, and we classify the pixels into, why today I have to stop this then. All have joined. Can you see my screen?
Yes, sir.
So what we do, one is in the per pixel classification, we are going to classify on the basis of its signature. And on the other hand, in object oriented classification, we are not only taking tone as a property, but we are also taking shape, size, texture, pattern, association into consideration to classify that earth object is as image segmentation or as spectral feature, that is object. And these objects are characterized both in raster and vector domain. So what we do generally, when you are going for object image classification, we are using a cognition software. And when you are going for per pixel classification, generally we are using ADAS, we are using unsupervised and supervised classification technique, where we'll be using the spectral signatures, spectral properties we'll be creating, and then we'll be classifying the earth object. But in terms of object-oriented classification, you will be running the various kinds of vectorization. First, what we'll do, we'll vectorize the image. The raster will be converted into vector, and then those vectors will be reclassified into various classes. So that's why we are saying in object-oriented classification, we are saying as objects. So these objects are classified both spectrally and spatially. So if you generally go with the digital image classification technique, the common techniques that are used for image classification is the per pixel method is supervised classification, unsupervised classification, and rule based classification. So when you are going for per pixel classification, two approaches we have said, one is per pixel and another is object oriented. So when we are saying per pixel, the classification technique will be supervised, unsupervised, and rule-based classification technique. So now we'll do in detail what do you mean by supervised classification technique. Supervised classification technique, the analyst means we supervises the characterization of a set of specific classes by providing the training statistics that identify each category. So what does it mean? It means that that we are familiar with the terrain, we are familiar with the object, we are familiar with the various features that we can identify on the basis of tone, and we are providing the spectral signature. So what we'll be providing, we'll be providing the spectral signature, and all that are also known as training sets. So what we do, on the basis of ground truth data or the other ancillary data, we are familiar with the object, we are familiar with the terrain, we are familiar with the area, and those features are used to identify as a training set, and those training sets are used as a samples to classify the entire satellite image. So that is known as identifying each category. So what you have to do, you have to identify each category, you will be creating the training set of each category, and on the basis of those training set, the entire satellite image, the entire pixels will be classified into specific classes. Whereas on the other hand, when you say unsupervised classification technique, here the human interference is less, and the computer generates itself the various classes. So what is that? The raw spectral data are grouped first. So what it will do, the entire values that you're getting in the form of digital numbers will be classified into various groups, and based on the statistical structure of the data. So what it will do, it will be classifying the entire digital numbers into various zones or into various groups like 0 to 100, 100 to 150, 150 to 200, 200 to 255. In case we have said you classify the entire image into 5 categories, so it will be grouping the entire digital numbers into 5 categories, and then the analyst must label each statistical cluster, placing them into appropriate category. Means what it does, then we'll be classifying, we'll be providing the different kinds of iteration to the image classification, and the pixels will be readjusted according to its group. Maybe if some pixel carries a value of 99, so the system will check whether it will go into group 4 or group 5. So that will be created, and the entire operation, the entire classification is based on clusters, means they are grouped into classes, and those classes are used to classify the image. Okay. And finally, you have got rule-based classification, where spectrally characterized pixels are classified using ancillary data in GIS model. So now we'll be going into detail about the supervised classification, as we have already started with supervised classification. So what do you mean by supervised classification? In the imagery, the analyst identifies homogeneous representative examples of various surface curves information classes of interest. So what we do, we identify the signatures of each and every sample of the earth, whether that is agriculture, which area is agriculture, will be getting the sample size as agriculture. So in your area, if you have got 4 types of agriculture, that agriculture 1 represents kharif, agriculture 2 represents maize, agriculture 3 denotes mango plantation, agriculture 4 denotes potato plantation. So we'll be training the our image through training sites, and these samples are referred as training areas. So what we'll do, we'll train our satellite image, we'll train our signature, so that those training sets or those examples or those samples will act as a catalyst to classify the entire satellite image. So generally, if you have seen that when you come for the best example is when you go for, you want to paint your walls of a room. So what you do, generally don't paint the entire wall directly. First you make different color combination, and then you check in a smaller sample size, and if it fits to your area of interest, you go for the entire walling and you go for entire painting of the wall. In the same way, in the image classification also, we will be tracking the various sample sites of each and every classes that we are going to identify in the satellite image, like what is the signature of wasteland, what is the signature of water, what is the signature of river and sand, what is the signature of build up area, what is the signature of agriculture, what is the signature of wetland, what is the signature of scrubland. So we'll be providing the training sets, and the features that are similar to those reflectance, those tone will be classified into various earth categories. So the selection of appropriate training areas is based on the analyst familiarity with the geographical area and their knowledge of actual surface cover types present in the image. So the accuracy of the classified image depends on the amount of knowledge that you have for that specific terrain. That's why this can also be said as knowledge based classification, where the interpreter uses its field knowledge, uses its ground knowledge, is familiar with the terrain, is familiar with the objects, is familiar with the various land use, land cover available in that area, and on the basis of that he will be classifying the entire satellite image, because on the basis of that he'll be training the training site, and on the basis of those training sites or training area the entire classes will be classified. So a good visual interpretation skills are mandatory for the success of supervised classification. So you can see that what we have done, this is a satellite images, and we have taken out the training sites, we have taken the spectral signatures we have created, like we have created a polygon that represents that this spectral green in color represents, that is a post classification image that was based on the training site. The training sites was conifer, the training sites was water, the training sites were deciduous plant. So on the satellite image, we identified these three different Earth objects, and we created individual signature from the satellite images. And on the basis of those training sets or training sites, the entire satellite image was classified into three different categories. That was deciduous forest, coniferous forest, and water. So the training sites are very important for the accuracy of your classified map. So you can see that how this spectral signatures are different for different earth object in different spectral bands, and because we were familiar with those bands, we used to classify on the basis of the known polygons, on the basis of the known signatures, we classified the unknown pixels. So when you are providing, you now you know that you have to provide a training set, you have to classify the images. So you have got various algorithm through which, or different classifiers, the classifiers are algorithms on the basis of which the training sets or the pixels are selected for the classification technique. So the common techniques that are used for classifier in supervised classification techniques are parallel pied, minimum distance to mean method, maximum likelihood, and a spectral anger mapper. So what does parallel pied means? That is based on the range or variance of the class DN value. So parallel are based on the variance. You have to calculate the variance of the various distal number, and on the basis of that, it will be classifying all the distal numbers. When you comes to minimum to mean distance, that is, we have to calculate the mean of each class value, and on the basis of that mean class value, we will be classifying the distal number. Then you have got maximum likelihood, that will be doing a more into the detail. This is only for the basic understanding. So maximum likelihood is based on probability of a class membership, and spectral anger mapper is based on the class membership based on minimum difference from n dimensional spectral vectors of the class. So what you have to do when you are going for a supervised classification technique, first you have to define the training data. Means each training site should appear homogeneous and representative of the lesion class. So already I have stated that you have to classify the satellite images, so you will be taking the signatures of each and every class that you are trying to classify. Like if you want to classify the entire images into 8 classes, so you have to classify what are those 8 classes, what is the signature of those classes, like what is the signature of agriculture, what is the signature of fallow land, what is the signature of water, what is the signature of vegetation or forest, what is the signature of wasteland, what is the signature of various other features that you want to delineate. And on the basis of that, several training sites for each legend class has to be taken. Minimum each training set will be at least 20 to 25 pixels. Okay, so minimum training sites that you are using on the basis of which each and every class will be classified. So you must take at least 20 to 25 pixels as a training sites, and each class should be represented by n number of spectral bands in the data sets. So that depends on your accuracy, that depends on your lesion, that depends on your classification. So what you do whenever you are going for the training site selection for band C, TM and ETM, the total number of training per class should be at least 600. That is, try to capture the landscape diversity of the class. That is, don't try to collect a big group of pixels. Like if you are creating a big polygon in an area, maybe the features or the signatures of other land use land cover class can be taken as a single class. So what you have to do, you have to take the pure pixels. Don't try to take unpure pixels. If it's not pure, what it will do, when you're providing the signature, it will take the signatures when you're thinking that you have taken a signature of agriculture, but maybe inside that agriculture signature, what you're providing as a data set, you have taken some build up portion, you have taken some water area. So what will happen, this signature when you will be using for classifying the image, the entire water bodies at some portion, the entire build up area at some portion will be classified as agriculture, because you have taken that as a signature site. So whenever you are taking the signature to classify any satellite image, you must obtain pure pixels that are very good samples through which you will be classifying it, and it will should be uniformly distributed throughout the area. Don't try to accumulate a large pixel at a single place and then you classify the entire satellite image. So what you will have, the entire image will be classified, but when it comes to the accuracy will be on the lower side. That is because you have not taken the pixel size from, or the training size from throughout the area. So just like geometric transformation, when you are geo registering any satellite image, you have to take the training sites from the various portion of the satellites. In the same way, when you are taking the training sites for classifying the satellite image, you must take it from different, from all the portions of the satellites, that is northeast, southwest, southeast, northwest. So you see what you have taken when you are trying to create, when you are trying to map a feature, you see this is a sample size that we have taken as a signature. So this is a pure pixel. If you take a smaller portion, you see there is no deviation and there is no other classes that we have taken that into consideration, and we have classified this as agriculture. For example, if you want to classify this as agriculture, so we have taken this as a training signature. But if you increase the training site of this area and you go to this blue portion, so that is taking the impure class into consideration for classifying the area. So always when you are trying to take the spectral response curve, always try to take a pure pixel in which there is no confusion and it doesn't take a signature of any other class that you are trying to classify. So you can see again how when you're taking a signature editor, so this entire operation right now what we are stating or what I am showing an example is the exercise that we are going to do it using image processing software that is known as ADAS, hexagon or intergraph, locally it is known as. So we'll be first taking the signature editor and we'll be classifying the name. So you can see what is the color, what is the spectral response curve, whether that is a single band or a multi-band image, and you can see the spectral response curve. So that is good. So that is a good sample you have created to classify the image. The other example, when there is a heterogeneous area, means there is in between, you have got a settlement area, you have got a water line build up area, you have taken agricultural land. So if such kind of features are available and you are taking a big sample size, so that is a bad signature, because your entire area, the sample that you are providing, it will confuse the system, and at last you will have a poor classified image. So whenever you are taking a satellite signature, always try to take the pure pixels, and the sample size should be smaller in nature, so that the mixing of classes doesn't happen. So when you are using the training sites, you can see that usually the training data should be normally distributed if the maximum classifier is going to be used. Means maximum range value, you have to use all the spectral that denotes from your 0 to 255. So you must take all the range value for classifying the image, and in supervised classification process, collect several training sites for each class in order to capture the landscape diversity of the class. So what we are trying to say is, the more if you are taking the signature of each and every class, whether that is a representative of a class at a darker version, or that is a representative of a class at a brighter DN value, the spectral mean and DN value and small variance will be taken into consideration, and the accuracy will be increased if the number of sample sites are more. For variables, classes do not merge signatures. So you can see that the disadvantage of the merge signature is the shifted mean DN values are typical of the class and have a large variance. So try to have a signature, try to have a image with a small variance value rather than having a large variance value. That will have a large variance value means the accuracy of the map will differ. So you have to how you will be creating, you will be going to the option in the ADAS image in 2011, you will go for the option drawing, you will be selecting it, and in drawing you will be selecting this polygon. These polygons are known as grow. You will be selecting this grow features in order to create the spectral response signature. So what you have to do, you have to select that option in ADAS imagine. You have to go into this option drawing, then you will be selecting this polygon that will be indicated as grow. And once you have taken this polygon, you have to select the pure pixels. So this is the pure pixels that we are taking, and then you have to provide the class name to this signature. This is known as spectral signatures or spectral editors, and the basis of this spectral signature or this editor, the entire satellite image will be classified into various land use land cover categories. So what you have to do, you will be taking this grow, then you go to growing properties, then growing properties, you will be going for the neighborhood operations. In this option, if you go, there is an option like growing properties. When you will select the growing properties, you select this neighborhood operation for classifying it, then you take area. So what is the area you want to take? 1000 pixels, you have to select this 1000 pixels, and minimum equal spectral distance is 15. Reset this to 1000 and reset this to 15, and again redo the entire exercise, so that to have a good spectral curve in that area. So using this region grow tool, what you can do, you can select a seed of pixels with the region grow tool, that is selected seed pixels, and this is the grow tool. So what you have done, you have excluded the area in between which corresponds to the other land use land cover feature. Maybe in between the some classes there can be some tree plantation in between some agricultural land. So you want to classify that tree plantation as a plantation category and the entire area as a agricultural land. So using this grow tool, if you will be generating it, it will be deselecting or it will be excluding the area that you have what generated as a signature, and this area will not be taken into as a signature when you are providing the signature to the
image. So using this region grow tool, you see how well we can classify the equivalent distance when it is 15, when it is 5. So you can see for a 8-bit data, if you are going for the 15 equivalent distance, the amount of accuracy of the selection of the data was very good, and the classes were very easily delineated and demarcated. But when you go and you reduce the equivalent distance, what will happen? There will be more heterogeneity in the class, and there is a lot of confusion. And many times the systems self classifies the same object into various classes. So that can create a confusion, that can create error in the image. So try to keep the equivalent distance as small. If you are creating it, that can create a problem. So try to keep that to a level that is 15 in number. So what you have to do, once you have taken that different sample size using signature editor, you will be saving it, and you will be classifying it for various art features. Like we have taken for agriculture, you will be providing the training sets, what are the training sets of agriculture. Then you have to take the training sets, what how we have done for settlement, in the same way for forest, in the same way for wasteland, in the same way for fallow land, whatever's come to your mind. And once you have done that, you have to select signature editor. So in raster option you will be going, because right now the exercise that we are trying to do is a raster based operation. So here you have got two techniques. When you will be selecting ADAS imaging, you have got two operation, that is unsupervised and supervised. Then you have got image objective, hyperspectral, subpixel classification, knowledge engineer, zonal change. So right now we'll be going to the supervised classification technique. And when you will be going into the supervised classification technique, you have to select signature editor, because right now the entire operation that we are doing is a representative of signature editor. So we'll be selecting the option signature editor. Once you have taken the signature editor, you have to, whenever you are growing the tool, whenever you are creating a polygon in an image, you have to select that polygon, and then you have to add this button. There is option of add plus. So when you will be plusing that image, the signature what you have taken in the satellite image will be represented in this signature editor. So you have to go on saving the value of each and every indicators, each and every classes in through this signature editor file. And you have to rename, you can re classify, you can give new colors. Like previously it was red in color, now I can say that red is an agricultural land. So I will type the name agriculture, and I can provide a color that is yellow. So this yellow color, when you will be classifying it, and when you will be classifying the satellite images using the spectral response editor, the entire agriculture by default will be classified as red in as yellow in color in the final output image. So this is the training size. How you can see, you can go to view, you can see the image alarm, what is the accuracy of the data sets. You can edit the data sets, you can calculate the various kinds of standard deviation, you can set the values of those parallel limits, you can indicate how much overlap you are interested in. So this all is statistics related operations. You can set your formula, what should be the standard deviation. So if you have selected the standard deviation 2, that indicates that standard deviation eliminates the darkest and the brightest 2.3% of the data. So you can see that when you're changing the mathematical value while creating the signatures, you can purify, you can take more accurate satellite signatures, so as the accuracy of the map will be very high when you are going for the signatures creation. So generally whenever you are trying to create a geo rectified or spectral response curve, you set the standard deviation between two, that is the 95% 0.4% of the data set, and 3 is 99.7% of the data set. and one standard deviation represents 68.3% of the data set. So the best operation or the best method through which the best value you can get a maximum accuracy, try to set the standard deviation as a 2, because that represents that indicates that 96% of the data sample value has been taken. So eliminate the most atypical values from consideration. So you will be taking all these data sets. So you see, then when we have taken that yellow color as a signature, all these colors, all these objects with the same spectral signatures are classified as yellow in color. Means gradually what we are doing, we are classifying the various tones and various earth object in an image into various land use, land cover categories on the basis of your spectral signature. So you'll be taking this signatures for each and every earth object, and finally we'll be providing, then we'll be omitting the errors that indicates need for and location of additional training sites to adequately capture the spectral variability of the class in question. So maybe we have taken the training set, but you can see that the entire area was lot more than what we have classified using the existing sample size. So what you have to do, you have to increase the sample size so that the entire area that you see in a satellite image is perfectly classified using those signature editors. So you have to increase the signatures. So what does errors of commission means? It indicates that the training site is not spectrally pure regarding the assumed land use, land cover. So what you have to do, the analyst must go back to construct the training site spectrally by editing the existing trailing polygon and drawing a new polygon. So what you have to do, you have to draw a new polygon. Generally, it's better to leave some pixels unclassified, that is also known as omission error, rather than having a large commission error. So now the different classifier that we are going to use are maximum likelihood probability classifier, then maximum likelihood without prior probability information. Then how does it works? I'll go directly to this portion, because that will make your things or the signatures what we are trying to say will be more classified, will be more accurate. So you can see that this is the two pixels that we have, that is one is indicative of this pixels are 1, 2 and 3. So what we have done, we are trying to find out the class values of 1, 2 and 3. Where is 1? You go here, 1 that is outside the household, then 2 that is near the railway lines, and 3 is near the outward. So what it does, depending in the probability, it goes on checking to the which class this object denotes to, and basic of their distance, the basic of their probability, this is classified into that particular classes according to the its probability, how likely it is to be associated with that particular class. So it will be classifying it using the probability which is the maximum condition which is nearest to which class, and it will be relocated on the basis of its location where it is located. So from known values we'll be classifying the unknown pixels. In the same way, you can see that how it looks like when your probability functions are being performed in digital image classification. So when you are using the maximum likelihood probability classifier, the advantages, it's sensitive to both variance and covariance of the data sets. A disadvantage is training data must be normally distributed. The per pixel rather than per a neighborhood approach remains a problem. So what we are trying to do, what is the error that you have seen, that we are trying to see that it's just an operation that was similar to that of a resampling technique where we are using nearest neighborhood by linear interpolation cubic convolution, that we see which pixel is nearest to the a closest output image, and we try to assign the same value to that output image pixel. In the same way, in the maximum likelihood also, we are not classifying on the basis of its pixel value, but we are seeing the adjacent value, what is the probability in which class it is nearest to which zone, and on the basis of that it will be selecting its class. So many times maybe whatever probability that we are providing using maximum likelihood may be a wrong class. So there can be a problem in classifying the earth object, and the accuracy of the data can differ depending on its objectivity, depending on your uh, inclination. So what you have to do, will be doing more detail into your coming classes. What you mean by maximum likelihood classifier, we'll be doing more detail into that. So today it's just a brief and overview of the entire classification techniques that we are going to do. Then what you will be doing, you will be selecting the supervised classification from your satellite images, and then what you will do, you will see the input image. Can you see the image? Can you see the screen?
Yes, sir.
So what you will do, you will provide the input image, then you will be provide the signature. So here what is the important, we said when we are doing a supervised uh, classification techniques, you have to provide the signature. So here we'll be providing the signature. Here you have to select the different kinds of decision rules that you will be using to classify that satellite images. Here you have got a non-parametric rule, you have got a overlap rule, you have got a unclassified rule, parametric rule. So here for the current operation, we have selected the maximum likelihood operation for classifying the satellite image. So you have to use the different options to classify that satellite images, and on the basis of different classifier, the different thresholding will be classifying the satellite images into various classes using the classifier. So that rejects the value, that classifies the value on the basis of various algorithms, and will be classifying the image simple size or the Excel size using its maximum likelihood, mean to maximum to mean distance. So all those classifier you will be seeing. You see here we have taken the different classifier. You have taken a spectral angle mapper. So these are the various techniques that we will be using to classify the image, and we'll be doing more into the detail in the coming slides. I'll be teaching you more details how it has been done. So the image classification can always be improved on the basis of your precise LULC categories. Per pixel classification works back with the moderate resolution with greater than equal to 20 meters. The classification process is iterative. It's here to have high classification after first attempt. So if you're generally classifying it at the first instant, it is not necessary that you will get a very high accurate image. It differs, it takes time, you have to go on increasing, and that depends on the more the experience you have, the more you experience and classify the different algorithm. You can see that how the accuracy will differ with your time. So that is a more that we have seen. We'll be doing much detail into the coming slides today. Just a overview. That's why I skipped some of the classes tomorrow. I'll be teaching you more detail into the various classifiers that we have used for your image classification. Today it was a brief overview of what are the different kinds of classification technique and how it's work. Now we have done with the supervised classification technique. Now we'll be studying the another classification technique that is known as unsupervised classification technique, where the raw spectral data are grouped first based on their statistical structure of the data. Then the analyst labels each statistical clusters, placing them into appropriate categories. So I've already said what it does. It classifies the image in its own on the basis of various classes, and then it is rechecked again to get a final classified image. So what does unsupervised classification requires? It requires only minimum input from the analyst. A lot of input is not required because you have to no spectral signature or no spectral set has to be given. So that's why the minimum interface is for the user. However, the analyst has the task of interpreting the many classes that are generated by unsupervised classification algorithm. So here also you have got various algorithms on the basis of you will be classifying the satellite images. So you have got unsupervised classification technique that is also known as clustering, because it is based on a natural grouping of pixels. So what it will do, it will be based on natural grouping, like from 50 to 0 to 50, 50 to 100, 100 to 150, 150 to 200. So that is known as a natural grouping of the pixels, and which are plotted in feature space. So the clusters are divided using clustering algorithm. The clustering algorithm has no regard for the contiguity of the pixels that define each cluster, unlike the training areas for the supervised classification. So the common algorithm through which you will be classifying your unsupervised classification technique is known as ISO data. ISO data and k-means. They are the two algorithms that are used in unsupervised classification technique. Their classifiers that we are using in unsupervised classification techniques are different from the classifier that we have used in supervised classification technique. Here we are using ISO data and k-means to classify. So what you do mean by ISO data? ISO data means iterative self-organizing data analysis. Iterative self-organizing data analysis means clustering method uses spectral distances and iteratively classifies the pixels. So the pixels are classified on the basis of spectral distances and classifies the pixels. So if for after each iteration, means after each we have generated a class. Now again after the next iteration, it will rearrange the class. Again after third iteration, it will rearrange the class so as to get the best clustering, to get the best group in the classified image. So after each iteration, ISO data redefines the criteria for each class. So after each iteration provided to the system redefines the criteria of each class and classifies the systems against, and gradually discovering the spectral distance pattern, the clusters in the data. So it will try to cluster the data and it will try to group the data into common platform. So initial cluster means are evenly distributed across the feature space along a vector that runs from multidimensional to multidimensional plus to minus value in an image, and until unless the entire pixels of the image are not classified. So each and every pixels uses ISO data uses minimum spectral distance to assign a cluster for each candidate pixels. The process begins with a user specified numbers of arbitrary clusters, means of existing signature. With each iteration, the mean shifts to those to the clusters in the data. Because ISO data is iterative, it is not biased to the top of the data file and are the one plus clustering algorithm. So the spectral distance between any candidate pixels and each cluster means is calculated, and the pixels is assigned to the cluster whose means is the closest. So what you will be doing, you will be generating the various clusters. You will be seeing how the data is clusters and generated using the spectral graph, and we'll be using the various clusters for identifying the data sets, for providing the iteration, for calculating the mean vector assignments for partition of the data set, and finally we'll be classifying the entire satellite image. You can see that how the when you are going for the different, this is the second iteration, this is the first iteration, how the data are being partitioned, how the data are being relocated, until unless each and every class denotes or rearrange itself to a particular class. So you can see distribution of ISO data mean vector after first iteration, that is the distribution of the brightness value, and this is after the iteration 20. You can see a more diversified, a more clearer object, a more uniformly distributed image. So all such kind of operations are self generated using ADAS imaging. So again, you will go to raster, you will go to unsupervised classification, and you will go to input image, you will go to output image. Then you will be selecting the methods. I've already stated there are two methods came in ISO data. So right now we are using the ISO data method for classification. Then you have to select what is the number of class in which you want your satellite images to be classified. So in the current image we have said that we want to classify this into 13 different land use, land cover categories. Then what is the minimum pixel size, what is the maximum standard deviation, what is the minimum distance, what is the maximum words, what is the maximum iteration that you want to give. All such data has to be defined by the user while providing the run function to the computer. And thereafter, when you're providing this all information, the satellite image will be automatically classified into various earth objects, where the step one is your satellite image, step two is your output image, step three is from initialized from the statistics or signature means, and four is ISO data. Step five is your rule that should be at least 3 to 5. Then minimum size 1 to 5%, maximum deviation 3 to 4%, then minimum distance 4 to 5 for 8-bit data, and maximum merge is 10 to 5 for the best operation. So when you are providing all these options, your iteration, your grayscale, whether you want to be a diagonal axis, you have to select. You have to select automatic. Then grayscale, you will be selecting. Then 15 to 20 iteration unit you will be selecting. Then you will be selecting the iteration size. What is the skip factor? So all such information has to be provided prior to classifying the image, and after each iteration the normalized pixels of the pixels whose assignments are unchanged since the last iteration is determined. And finally a quality check has to be performed to provide the thresholding so that the maximum accuracy is obtained in each and every operation. So you see the algorithm, what is the accuracy. So you see with the more number of iteration, the accuracy of the data increases. So you keep this conversion threshold as 0.957. And finally you will see 20 classes clusters with 6 iteration. This is the satellite images, and on the basis of unsupervised classification technique, post providing all the data sets, all the input, the entire satellite image is finally generated, and we are getting a classified satellite images. So this is the input image, and this is the output image that the computer has generated automatically with all the input parameters that you have stated while operation. So we'll be doing this all exercises in our labs, and we'll be providing this all attribute, the color options while classifying the satellite image, where each and every black and white color is indicative of different earth objects. You can see this number are the various kinds of pixels and what are the reflectance, and here you will be providing the names to each and every classes, which class this different earth objects belongs to, and you will be classifying the entire satellite image. You can export, the option is there: edit, format, report, import, export, formula, color. All the options are available with you, and you can use this attribute table to classify the entire undefined values. And finally you can see that how after color you provided yellow, the entire pixels with the same pixels value are indicated with a yellow in number. So you can repeat this entire operation in the image, and finally you will be getting a classified in this image. So this is a cluster based image, and tomorrow we'll be doing more in detail classification techniques will be doing related to your clustering exercise. So today we have seen that how the satellite images in detail will be more doing to that how will be doing what are the techniques. But at least today now we know that why what do you do mean by image classification, what do you mean by soft classification, what do you mean by hard classification, what are the different object oriented approaches, what are the post pixel based approaches, what do you mean by supervised classification technique, what do you mean by unsupervised classification technique, what you mean by object based classification techniques, what are the different kind of classifiers that are we are using in supervised classification technique, what are the different kinds of classifier that we are using in unsupervised classification technique, how they work, what are the mathematical consideration that you have to check, what are the techniques that has to be adopted. So each and every system has got some positive and negative. So I think that we'll be doing more labs, we'll be reading more in detail about the various image classification techniques, and over the coming months and coming days you will be post classifying, we'll be doing classifying a lot of satellite images, and we'll be seeing that how the accuracy has to be improved while doing various kinds of classification in your satellite images. With this, I end my today's class presentation of digital image classification. And now we'll have our 10 minutes of group discussion followed by your quiz in LMS. And with this, I end my today's class as a recording.